So to follow up on the previous video about solving systems that have only two variables in them, the other method that we have is referred to by two different names, either the elimination method or the addition method. And between those two names, what we actually have are pretty much the basic guidelines of what we would like to do. We would like to eliminate something, and we would like to do so by adding. So, if we're talking about only two variables, we'd like to eliminate one of those two variables. That would leave us with an equation that had only one variable in it. Good. We would like to do so by adding, because adding is a whole lot more direct than, for instance, subtracting. A lot less that we might have made a mistake accomplishing when we add versus subtract. So, between those two names, we got that general idea of what we want to do. So, as far as the first step, we're going to choose whichever variable we would like to eliminate. Now, we want to do that by kind of keeping in mind how we're going to do that. So we really need to have an understanding of the second step and then the third step in a manner of speaking as well, so that we can make the best choice between whatever variables we have. With step 2, we want to adjust either one or both of our equations, because it's not very often that we're lucky enough we don't need to adjust any of them, and we could just directly add things and eliminate one of our variables. So more than likely, we will have some amount of work to do where we adjust either one or both of our equations. Now clearly, if there's a way to adjust only one, that's preferable to having to adjust both. So that might inform our choice. If we have to adjust both, whether we pick one variable or the other, is there maybe an easier path to take? One of the variables is easier for us to adjust both equations, while the other one is not quite as easy or direct to do. So this is going to have some manner of influence on the decision that we would make really in step 1. You're going to see a little bit of that when we get to some of our examples. Now, once we've made those adjustments, we should be able to add our equations together. Now, there's the distinct possibility that we will not end up with a variable showing up. And so we have the same sorts of statements that we had made before about whether we're going to have infinitely many solutions or if we're going to have no solution. But for most of the work that we're going to do, we'll end up adding those equations together and getting one variable showing up. The variable we chose in step 1 should be gone. By having an equation that has only the one variable, we now have a much more favorable situation. We have an equation that's much nicer for us to solve. So we go ahead and solve that, and that gives us half of what should be our answer. We're going to take that, we're going to go back to one of our original equations, and we're going to figure out the value for that variable we originally eliminated. Once we have both of those values, we can check, verify that we do in fact have the correct solution, and report that. So let's take a look at an example here where we have those steps mentioned, and let's try not to go too far along before we don't have our steps written up on the screen any longer. With the first step, we want to choose which of our variables to eliminate. And in step 2, we're saying we're going to adjust one or both of our equations so that we're going to have the same number with opposite signs in front of our variable. So if we look at this particular example and we consider the x's, we've got a 2x, we've got a 3x. So one of the things we're going to need is opposite signs. So one of these equations is going to have to transform into a negative something x. We also have two very different numbers. These aren't related to one another, so we would have to make adjustments to both equations. So there's a little bit of work involved there in adjusting each of our equations so that they'll have the opposite numbers in front of the x. If we look at the y, is there anything more favorable about that? Well, the y stuff already has opposite signs, so there's that little bit that's going for it. But better yet, the first equation just has that minus y, while the second equation has a positive 2y. That means that we can get away with only adjusting that first equation so that it would have not only the negative, but then a 2 out in front. So that's less work than if we were to choose to eliminate the x. Now, you're welcome to do whichever one you would like to do. But what I'm suggesting to you is just a way that you can try to decrease the amount of work and effort that you have to put into the actual process here. So in this particular example, we're going to follow that suggested manner of thinking. We're going to eliminate y because it's only going to require us to adjust that first equation so that we can get a 2 in front of the y. We're going to multiply everything in that equation by 2. So 2 times 2x gives me 4x. 2 times y gives me that 2y. 2 times 4 gives me 8. And that second equation we're just going to keep the same. Now we can see over there with those equations on the right side, we can add those together, and when we do, we'll get 7x. The y's cancel out. So 7x equals 7. Well, very quickly then, that means x is equal to 1. And using that particular value, we can now figure out what y is. We'll go back to one of our original equations. So, just for the sake of argument here, we'll use the first equation. Again, you could just as easily have chosen to use your second equation and plugged in the x equals 1. Solve for y, you should get the same thing either way because we should have the right answer, provided we haven't made any mistakes. But because we're human and we always can make mistakes, this is what our solution should be, the 0.1 comma negative 2. So we would want to go through and take advantage of our very good situation of being able to check that particular solution, or check that answer, and verify that it is the solution. So checking that in the first equation, everything works. Checking it in the second equation, everything works. And so we can confidently say that our solution is in fact that 0.1 comma negative 2. Now, same kinds of steps. Take a look at another example here. Just to be different from the previous example, let us eliminate the x this time. So for no other reason than to just have a different example than the one that we just finished. We're going to eliminate the x. That means that in this particular case, we would be looking at the 3x plus 4y equals 17, and we would be looking at the, excuse me, 2x plus 3y equals negative 2. If we would like to come up with the same number in front of the x, since we have a 2 and we have a 3, then the quickest thing for us to do would be to create a 6 in front of the x. So we'll go ahead and we'll multiply the first equation by 2, and that'll give us 6x plus 8y equals 34. In the second equation, we want to multiply, and not only do we want a 6, but we also want the opposite sign. So we'll go ahead and multiply by a negative 3. That way we can get a negative and a 6 out in front of that equation. So negative 3 times 2x is negative 6x. Negative 3 times 3y is, negative 9y. Negative 3 times negative 2 is 6. Now we can go ahead and add those together. So the 6x plus 8y, and you might feel this a little overkill that I could have just added those the way that they were originally written. And you're right, but we're being a little overly cautious here. as we are getting in the swing of things. So 6x and a negative 6x will cancel out. 8y and a negative 9y will give us negative y, and 34 plus 6 will give us 40. So what we're really looking at here is that y would be equal to negative 40. Now that's, again, what should be half of our correct answer. I want to take that and come back to one of my original two equations here, and I want to figure out the x value for my answer. So if I want to find the x value, again, we can be a little different from what we had done in the previous example, and this time we can choose to use equation 2. So, in the second equation, we have 2x plus 3. Instead of y, now we believe that that should be a negative 40, equals negative 2, meaning that we would have 2x minus 120 equals negative 2, which means that we would have 2x equals, adding 120 on both sides, 118 is equal to 2x, and therefore it would seem that x is equal to 59. So the solution should be and we want to make sure that we're careful. We found y first, but we still always list the x value as the first value in our pair. So the solution should be 59 comma negative 40. And again, we can check and see what's going on here with that. If we do the 3 times x plus 4 times negative 140 equals 17, and the 2 times x plus 3 times plus 3 times y equals negative 2. We should be able to determine that we are in fact correct. So the 3 times the 59 minus the, or times the, plus the, geez, I'm having a good time today, plus 4 times negative 40, we should be able to verify with our calculator that that is in fact correct. And then the 2 times the 59 plus 3 times negative 40 should verify that that is equal to negative 2. So again, you really want to be thorough about it. 3 times 59 plus 4 times negative 40 equals 17. 2 times 59 plus 3 times negative 40 equals negative 2. So those are in fact correct. Yay! And so we can go ahead and list our solution as being verified to be the point 59 comma negative 40. Now, of course, we can get fractions and decimals that show up, and so that might influence the sort of adjustments that we might make. For instance, in order to get rid of the fractions in this first equation, because it would just be a little bit more convenient to us to do so, we might take that first equation, multiply it by 6. And when we do, we actually happen to get a negative 2y. In comparison to that second equation that has a positive 2y on the left-hand side already. So we could automatically add those together. So automatically we would be able to eliminate the y with any additional work simply because of our natural preference to clear those fractions out of the way. And we get a 3x equals 3x, which is true. So according to the comments that we had made before, we would have infinitely many solutions. And we would need to have some sort of version of what those solutions look like to be as thorough as possible. So we can say different things like any point that's on the line 1/2 x minus 1/3 y equals 1/6. Or we could say any point that's on the line 2y equals 3x minus 1. Or if we rearrange things and had that slope-intercept form, any point that's on the line y equals 3/2 x minus 1/2. And so we could also give a solution set, which we've seen in a few other occasions, and we're basically given that line, because it's all the same line, any version of it that you would like, as long as it's a correct version of that line. Again, it's really just one line that they gave you in that original system. But this is the solution set style option, where it's literally a set. And the second option would be to kind of give a point in the appearance of x comma y. And with the way that things are working out here, we could say, pick an x, here's this y equals 3/2 x minus 1/2, and so, well, that's the way that we can get the y value. So we can crank out different versions of some of those infinitely many solutions, and the way that this is written is kind of already in that point notation. So we could do this as well. So it all depends on what you might like to give or what you might be required to give as far as the directions in your particular example. But again, the goal there, elimination or addition method, the two names together, telling me I'm going to want to eliminate one of my variables by doing some sort of addition problem, and that kind of gives me a little overview of what I'm going for. Same sort of comments apply that we've had. If we get an answer, we want to check it. If we end up getting some sort of always true statement, we would have infinitely many solutions. Alternately, in a different example, if we had some sort of situation where we added things together and had a false statement, then we would end up having no solution for that particular system. So all those same sorts of comments apply.